In this video, we're going to talk about our project step number 3. Now, let me call up the project steps and we'll take a good look at what we need to do with this. It says to produce a Newton Raphson solver for use with the Ramberg-Gaussian equation and the strain life equations. That could be the ones that are modified by the mean stress of x. Or learn how to use equation solvers in your programming language as applicable. So if you're using MATLAB or maybe you're doing something in Excel, there are probably built-in equation solvers that you can use. If you're using some other language, then Newton Raphson is fairly straightforward and it works pretty well for the equations we're going to look at. So we're going to talk about that in this particular video. Then it says implement case 1 hysteresis loop calculator for several levels of strain. In case 1, we'll get into more details later, but case 1 is a fully reversed constant amplitude loading strain controlled, and then as we discussed in class. No report is required, but please do seek assistance as needed. So let's talk about our equations and Newton Raphson in this particular video. I'll probably shoot a different video where I do the programming of it. Alright, so we have two equations that we've been working with. One is the Ramberg-Gaussian equation. So epsilon is equal to sigma over E plus sigma over K. Let's call it K prime, 1 over N prime, using the cyclic stress strain curve. So this is the monotonic, or the first branch. And then we had, I'll write the full thing over here, the hysteresis branch equation, delta epsilon over 2 plus delta sigma over 2 over E plus delta sigma over 2 over K prime to the 1 over N prime. Of course, this is just using the same functional form, but with Massing's hypothesis that says we expand the stress and strain, we have the same functional form with stress and strain amplitude. Now, the way we really end up using this is solving for delta epsilon. So if I do that algebraically, I'll multiply both sides by 2. The 2 cancels out with a half right here, so we have delta sigma over E. But then we can't do that. This 2 doesn't cancel out. It has to be a 2 times this quantity, delta sigma over 2 over K prime to the 1 over N prime. Okay, so this is the branch equation. All right, so what we can do with these two equations is we can go from, on our stress strain plot, we can go from 0 stress and strain up to some maximum value using the branch equation, or using the monotonic equation. And then we can use the branch equation to use this and bring it on down to here and so forth. Okay, so both of these would be using the branch equation. With the tip at the end of the last segment, with the sign of the delta epsilon either being negative in this case or positive in this case, depending on whether we have an upslope or a downslope in the next step. So what we have then is we have, if we repeat this, basically what this is a strain controlled, and I know it's not completely symmetric, but it's supposed to be strain controlled, constant amplitude, time history. And so I would like for you to demonstrate this with a computer program that you can do this sort of calculation. Now here's the tricky part, and this is why Newton Raphson needs to come into this. The tricky part is these two equations, the monotonic equation and the branch equation, those cannot be solved analytically for the stress. we're going to be given the strain. We're going to do strain controlled type calculations, and we want to solve for the stress. You can't do it analytically. We're going to have to use a root solver or this Newton Raphson technique to find the roots of our equation. Now at the end I'll also talk about the strain life equation as well, and we'll see how we have to use that to find the number of reversals to failure given a strain range or strain amplitude. Alright, so let's talk about this technique. Now for simplicity, we're going to just start off with the monotonic equation, but the same sort of things will apply to the branch equation, and we'll probably end up doing both. But let's focus in on the monotonic equation first. So our equation is epsilon is equal to sigma over E plus sigma over K prime to the 1 over N prime. The things that we know are the material properties, so we'd have to know the modulus of elasticity, the strength coefficient, and the hardening exponent. We would also know the value of the strain. Okay, so in general, if you have a function, let's say y is a function of x, and we wanted to find out what are the roots of this function, and this y is some kind of constant. Well, what we can do is we can rearrange this and have like f of x minus this constant equal to 0. If we were to happen to guess, just plain out guess, the correct value of x that goes in here, and we cancel out that functional value with our constant, and that equals to 0, then the guess that we would have made for x would be the root to f of x. That would be something that would solve this equation. Alright, so let's see if I can make a plot. Okay, so I have to be a little bit careful here when I show the axes. On the vertical axis is the whole left-hand side, the f of x minus y, and on the horizontal axis is my value of x. So the place where f of x minus y is equal to 0, right here, corresponds to that particular value of x being the root. Now this isn't the only case that could happen. There could be a situation where we have maybe something like this, and this never gets down to 0. Okay, that is a possibility. There could be a possibility where we have multiple roots. I'm talking about in general terms. But for our equations that we're going to look at in our class, there's only going to be one root. And it's going to be pretty obvious if there is no solution at all. And in our cases, it should have only one root to it. So this Newton Raphson iteration technique is pretty convenient for the work that we're going to do. All right, well, how does it work? Okay, so like I said, it starts off with a guess. Okay, so you put in your value for x into this function, you subtract off this constant term, and chances are you're not going to guess it right. So you're going to get a residual. Now, if we notice in this plot with the blue, you can kind of see the slope that goes through here. It could be steep, it's not going to go vertical. Vertical would be kind of a problem because that would be a function that gives you the same root for any value of x you put in there. That's not the kind of function that we've got. So something to do with the slope is kind of interesting. So what we're going to need to do is we're going to take the derivative of this entire equation here. Okay, so we're going to have an f prime of x, and of course this being a constant, the derivative of that's going to go away. So we're going to make a new guess, and our new guess is going to be based on our previous guess minus our f of x minus y. So maybe we should call that our residual. I don't want to get just the one term confused with the whole left-hand side. And we're going to divide this by the derivative. Okay, so then our new guess is a modification of our previous guess. If for some reason we were able to guess the right value on the second time, this residual would be 0, and so we wouldn't have any modification to our guess. Our new guess and our guess value would be the same. However, if this new guess isn't very close to solving this equation, f of x minus y, the constant, equal to 0, then we do get a modification, and then we get a new value for the guess. Well, then what do we do with the new guess? We go back and we plug it back in, and we keep iterating on this until we get our residual, you might say, equal to 0, but really it can be very hard to get it exactly equal to 0. So what we're going to do is we're going to put a certain limit on this. If it's a number of reversals, we might say if we're within 10 reversals for the strain life equation, then that's good enough. If we're within maybe 0.1 microstrain for the Ramberg-Osgood equation, then that might be good enough for that. Okay, so that's the basic idea. We're going to take a look at this equation, then I'll bring up then the branch equation, then the strain life equation, and I'll bring up a spreadsheet that I've mentioned in class already that you can take a look at and kind of see how this all works out.